Okay, in this video I'm going to continue on with my tutorial videos on thermodynamics and statistical mechanics. So we're on video number 5 and we're going to talk about adiabatic processes. The previous video was on the ideal gas law, which in this case actually is quite relevant. So we need to start somewhere, and I'm going to do a small bit of revision. First of all, the internal energy for a system, the actual internal energy, follows the equipartition theorem for most systems, and the equipartition theorem says that we have a half kT kinetic energy per degree of freedom. So there's the half, there's the number of molecules, then we have the number of degrees of freedom, and then of course kT. By the first law of thermodynamics, the change in internal energy is equal to Q plus W, where Q is positive as work if heat goes into the system, Q is negative if heat comes out, and the work done is positive if work is done on the system, and it's negative if work is done by the system. Note of course here that it's the actual internal energy, and here is a change in internal energy. This is very important. So remember, in our previous video on compression work, we said that work done is equal to minus the integral of P dV, and we subbed the ideal gas law into this, and we got that work done is equal to nKT, the natural logarithm of VI divided by VF. Okay, so that's my revision done. Next, let's define an adiabatic process. An adiabatic process is when the Q, or the heat input or output, is equal to 0. That's it. Simple. There's no need to be afraid of it. Adiabatic is just a word you learn. What it means is very simple. Q is equal to 0. So what does that mean? Well, delta U, the change in internal energy, now just becomes the work done. Alright? So I'm only going to talk about compression work in this case, because I'm going to use the formula for compression work. If it's electrical work, of course, none of these formulas will actually work. So we're talking about adiabatic processes where the compression work done is, the work done is compression only. So we said the work done is compression. We have adiabatic, therefore Q is equal to 0. Therefore the change in internal energy is the compression work. A moment ago I said that the internal energy, the total internal energy, was a half N times F times K times T. So I'm going to do a small bit of revision here on your calculus, where a function, let's say G is a function of, let's say, more than one variable, A, B and C. How do we get the change in G? dG, this is by definition, is del G del A times dA plus del G del B times dA. In actual fact, I'm going to just put it as two variables because that's all we need, and so on. Okay, so we take the partial derivative with respect to whatever the variable is, and we multiply by the total derivative of that variable, and that should make sense. It should make physical sense to you. What this means is, if we move an amount dA, well, the amount by dG changes is dA multiplied by the amount it's supposed to change by, the derivative. So every time we move dA, every time we move 1 unit, we add or change G by this much. So if we move dA units, we need to multiply by the derivative or the change as well. So that's a small bit of calculus. Why am I using that? Well, because to be honest, it's seen everywhere in thermodynamics. That means we know that U is equal to 1/2 NF KT. Therefore U is equal to U, a function of T. The only thing really that changes there is T. So that means du is equal to del U del T times dt. Okay? So del T of U is equal to 1/2 NF times K. And therefore du is equal to that. Okay? If you want, you can think about it as just getting du dt and bringing up the dt. But to be honest, that isn't what has happened. If you have more than one variable, it's better to think about it in terms of the rates of change and multiply by how much change has been made. Okay. The reason I need to get that is because we need a du here. But if delta U is small, then we can approximate it as du. Okay, so du is equal to 1/2 nfk times dt, and that's equal to the compression work W. Alright, so what's that equal to? Well, it's equal to minus p dv. Alright, so now we can say is 1/2 nfk dt is equal to minus p, and just bear with me, I'm going to put dv out here. Now, in order to integrate this, I told you we often need to get p as a function of volume. So look at the ideal gas law. So that means p is equal to that. That's p a function of volume. So I can plug it in here. nkt over v. Right, we have some constants we can get rid of. n, k. Get rid of those. What we're left with is 1/2 f, and we're going to integrate dt from t initial to t final is equal to, sorry, there's a t over here, I brought down that t. And here we're going to integrate from v final to v initial of dv over v. Okay, this is pretty straightforward stuff. They're both natural logarithms. So you're going to get this constant times the natural logarithm of tf minus the natural logarithm of ti. And here we're just going to get the logarithm of volume vf minus the logarithm of vi. You might be wondering why I'm going through this in step by step. I just think that it's probably best that we see this step by step. Okay, so basically what we're going to get here is f over 2 log tf minus f over 2 log ti is equal to minus log vf minus log vi. Okay, and the form we're going to try and get is t to the gamma vf, or tf vf is equal to ti vi, and then some sort of an exponent. Gamma is just some sort of exponent. That's what we want. So in other words, I'm going to try and put the finals on one side and the initials on the other. So let's go ahead and do that. We can rearrange this particular function here as follows. The natural logarithm of tf over ti, because two natural logarithms subtracted, you can have them as a quotient. I can bring then f over 2 up as a power. That's just your rules of logarithms. And here, this is something similar. We have vf over vi, and we bring up the minus from outside. But if we bring up the minus, we can instead just swap the signs here, or swap which is on top and which is on the bottom. Pretty straightforward. How do we get rid of the natural logarithms? Well, we exponentiate the whole lot. And we know that exponentials and natural logarithms are inverse functions, so that they just go away. And what we're left with is tf over ti to the f over 2 is equal to vi over vf. Or finally, tf to the f over 2 times vf is equal to ti to the f over 2 times vi. If you want to, we'd get rid of f over 2 and just call it gamma, and we're call gamma the adiabatic exponent. So this formula only applies when you have adiabatic, so therefore Q is equal to 0, and you only have compression work. However, it's still not in the form that's most commonly used in thermodynamics. So I'm going to do it. I'm going to rechange this, or re-evaluate this and put it into a new form. What we want really is to say that PV to the gamma is equal to a constant. When you're talking about adiabatic systems or adiabatic processes where only do compression work, PV to the gamma is a constant, and that's what I want to show you. And that is our most useful quantity. So let's go back what we said a moment ago. We said that TF to the F over 2 VF is equal to TI to the F over 2 VI. Okay, but we know that by the ideal gas law, T is equal to PV over N times K. So we can rewrite this as follows. So we have PF VF divided by NK to the power of F over 2 times VF is equal to pi vi divided by nk to the power of f over 2 vi. These two here are constants in the bottom, so we can get rid of those straight out. And notice that we have a vf to the f over 2 times a vf, we have vi to the f over 2 times a vi, we have a pi to the f over 2 and a pf to the f over 2. So let's rewrite this. Now, all good, we're doing well so far. Now the next thing we need to do is note the following, that 2 over f plus 1 is equal to 2 plus f over f is equal to f plus 2 over f. Just note that, it's just a small bit of perhaps useless algebra, but we'll see, it's actually quite useful. So what we're trying to do is we're going to get pv to the gamma, so we need to do something. We don't want p to have an exponent, so we need to get some sort of a root, and the root we're going to get is the 2 over fth root. So think about it, if you want to get the square root, it's the same as multiplying by the 1 over 2. So I want to get the square root, I multiply the power by 1 over 2. So in order to get, I want to go from f over 2 to 1, that means I need to multiply by 2 over f, or get the 2, I need to get the f over 2 root, if that makes any sense. Okay, so that's what we're going to do. We're going to get the f over 2 tooth root. So it's going to become pf, vf to the 2 over f is equal to pi, vi to the 2 over f. And if you add these two here together, you're going to get pf, vf to the f over 2 over f is equal to pi, vi to the f plus 2 over f. Now, a small bit of mathematics. If two functions are equal at any time, they must be equal for all time. So that means they're equal to a constant. And instead of writing f plus 2 over f, we'll just call it a placeholder gamma. And if we look, what we have here is that pf, vf to the gamma is equal to pi, vi to the gamma is equal to a constant, or pv to the gamma is equal to a constant. Okay? So for adiabatic processes, which means Q is equal to 0, where you only do compression work, pv to the gamma is a constant. And that's a good way of measuring thermodynamic processes. So, thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.